Hello everyone, welcome to ARM through C, where we learn the assembly language by C code. Last time I've made kind of a long introduction into functions, because functions in assembly are not supported directly, but the compiler creates them with branching special memory management called the stack. And I can sort of introduce the stack by first introducing very simple memory management technique, the ones that you would think of from the top of your head, but they're not very efficient. But we kind of introduced some basic problems that we're facing regarding jumping. If you want to refresh your memory or you haven't yet seen the video, you can click at the link above. Anyway, this time we're gonna jump right through into the code. We're going to see in the guts of the microcontroller, we're going to see the registers and the memory and see step by step how branching, the stack and other stuff is put together to make the illusion of functions, I would like to say, enjoy, but it's going to be a painstaking endeavor. Stick in. Here we have our C code, our assembly code, the general purpose register, as well as some special bookkeeping register that I'm going to introduce. In addition, I have the memory layout so we can look at the guts of the microcontroller as we step through the program. This will be clumsy at first, but once you come to terms with a few concepts, it is really simple. I mean, it must be simple because individual operations are really basic. We are still just shifting around data and doing simple math operations as before. The stack really works by starting at the bottom of the memory addresses and works its way up. In our case, it will start at the 020017FFF address, which corresponds to the last address of the 96 kilobyte area for this microcontroller. I will just start by going through the assembly steps and introduce concepts as we go along. First, we have the push instruction. This is an instruction that puts the value listed in the curly bracket to the stack in the opposite order that they are listed. It also updates automatically the register that we are going to introduce first. This is the stack pointer. The stack pointer simply contains the memory location that push is going to write to by first subtracting 4 bytes. So if the stack pointer is at 18,000, I'm dropping the prefix here, the push R7LR will first write at the 17FFC, the link register, introduced shortly, and the value at the R7 register to the address 17FF8. The opposite instruction is the pop instruction that takes the values from the stack and puts them into registers. The stack pointer is the first of our 4 bookkeeping registers that we need to work with the stack and function calling. Could we have the stack without push and pop? Yes, we would have to calculate the current location manually and use a register to store the value. Push and pop take care of the indexing automatically. We stack the values into memory with push and remove them with pop. You can consider them as syntax sugar of the assembly language. So push R7LR will first store the so-called link register to the last memory location, and the R7 register to the before last memory location, as you can see in the memory window here. But what are LR and R7? The LR is the link register, but it might be better called the remember the next instruction address in flash when branch is called register. Whenever we will branch into a function, the link register will tell us where to jump once the function executes. The R7 is by convention called the frame pointer. This register also does not have the best possible name in my opinion. Together with the stack pointer, it creates a frame for the variable of the function currently called to live in. This will be clearer as we step through the example. And since I've introduced 3, I will introduce also the 4th bookkeeping register here. This is the program counter. This register simply contains the location in Flash of the next instruction that is going to be called. It might be better called program instruction index, but program counter is not too far off. Notice that the stack pointer was decreased by 2 words, 8 bytes, when executing the instruction. Next line updates the stack pointer by subtracting 8 bytes. This will move the stack pointer 2 words up. We now add the stack pointer plus 0 and write it to R7, our frame pointer. This basically stores the stack pointer in the frame pointer, that's the R7 register. All memory manipulations within the main function will now be done relative to this address. Now we can breathe a bit. We have a move wide instruction of the literal value that will be eventually passed to the area function being stored to the R3 register. The R3 register is then stored to R7 offset by 6. Take a pause and observe the program counter and the values changing in memory. Oh yes, the memory offset is in bytes, not words, and values are stored in little endian, meaning that the least significant byte is stored at the lower address. So 0x1234 becomes 0x3412 in memory. The next 2 instructions do the same for height of the area that will be calculated. Observe again the program counter incrementing. Now both values are in memory, but at the end we must put them into R0 and R1 registers, where the area function will expect them by convention. This is done in an awkward way by first placing them to registers R2 and R3 and only then placing them finally to R0 and R1. To enter the area function, we do a BL instruction. BL means break with link. It does 2 things. The program counter jumps to the flash address of the area function and the link register. Remember the link register I called remember the next instruction address in flash when branch is called. Now that register now contains the value of the instruction that will come right after the branch instruction. We are now entering into the area function, and the link register contains the address where we must return to when we will exit. What do we do with this value now? What if another function is called within area and this link register will get overwritten? Well, we better save it into memory by pushing the link register content to stack. Also, we push the frame pointer to the stack and update the frame register again, so we do not overwrite main stuff, but rather reserve 16 bytes for the area function to use its own scratchpad. Let's take another pause here. Although we are only 50% into the program, we are more than 90% done conceptually. I really congratulate you if you've made it so far. Next, we copy the parameters that area rightfully expects at R0 and R1 and copy them to memory relative to the new frame pointer. Both values are copied via the R3 register. Just before calling convert units, the first parameter of area is put into R0. Now branch with link is called again. Observe the link register changing again to the address after the first convert units call within area. Now the first instruction in convert units is push R7. So only the limit of the function frame is saved, but not the link register. Why is that? Why is this different from the area function where both were called? Well, this is because the compiler knows that convert units will not call any other function, so there is no need to save the link register. We do have to reserve 20 bytes by shifting the stack pointer and frame register. We do the usual dance with the parameters, multiply by 100 to get the centimeters, and we move the result to register 0 where it is expected by convention. And now the important part. The function is done with the calculation and it must unwind the stack by recalculating the previous stack pointer and frame register to values before the function call. This way the area function can calculate its offset as they were before calling the convert units function. Now we jump out of the first call of convert units back to area and observe that the R7 and the stack pointer unwinded to the previous values. After exiting, the value is expected at R0 and it is saved into memory by the area function relative to the restored frame pointer at register at R7. We replay the second call by first preparing the R0 register with the parameter, which does exactly the same, except for the value of the link register will now point to the instruction after the second call of convert units. Both the calculated values are stored at 12 and 14 bytes relative to the area's function area frame pointer. We poke them out by loading them to R2 and R3 registers and finally calculate the area. The compiler is very pedantic. It stores the result into location 8 relative to the frame pointer only to copy it back to the same register and finally moving it to R0 when main will expect it. As in convert units, area also restores the stack pointer and R7, but also updates the program counter by popping the link register from the stack. Now area exits and the result is saved to R3, but then cleaned by writing 0 to it since nothing is done with this variable. At the very end, the stack bookkeeping is performed in the opposite direction as at the beginning, even though we are in the main function. Finally, we break out of main. There you go. We successfully called a function within main. Next time I'm going to compare how the if statements get translated in comparison to case switch statements. So stay tuned, subscribe maybe. And if you have an idea what I might try to compile and explain, write in the comments. Thanks.